So we use my favorite learning. So I think this class will not be recorded properly because I am using my computer, not the Zoom. So okay, so let's start. So sorry for the wait. So what did we learn? So actually after the long weekend, this is the first day after the long weekend, right? So what did we learn? The previous class, we learned about memory instructions, right? So what do memory instructions do in the RISC-V and RISC-V computers? Transfer between name memory and register file, right? Classify, so we can classify memory instructions into two types, boot and stores, right? Instruction data from memory to register file, right? And then store instruction, transfer data from register file to memory, right? So you need to remember. And then, so we learned about the endianness of RISC-V. Okay, RISC-V uses little endian memory system. Okay, and then also you need to understand the byte address. Most computer system use byte address. So it means address 1 occupies 1 byte of data, right? Okay. So so we learned about so we learned about some signed and unsigned instruction, and then we also learned how to generate constant. Okay, so let's learn about the logical and shift instructions. So, program languages that we can frequently use instructions. So what is the meaning of logical instruction? What is logical? What is a logical operation? So we learn. So if we took the logic design course, right? So the code is so we learned about the logic gate, right? AND gate, OR gate, exclusive OR gate, right? So logical operation. So logical operations represent the AND operation or basic logical operations such as the AND or exclusive OR NAND operations. And then the processor, actually the processor handles digital data, right? So binary numbers. So which means that the processors can support logical operations like the AND or exclusive or NAND operation. Also, the computer processors can support the shift operations. Then, in a programming language, we can frequently use these shift operations, right? We just the positions of bits in a data, right? That is the shift operation. So, for example, in C, we can use the this operator. Okay, also we can use this operator. So we can use this operator for shift left operation. Then we can use this operator as the shift right operation. And so we can find another operator here. The operators represent bitwise AND and bitwise OR, bitwise exclusive OR, and bitwise NAND operation. Okay, that is the bit by bit logical operations. Okay, so firstly, let's see the instructions in RISC-V. So RISC-V also supports bitwise logical operations. So this is the bitwise. Bitwise means the bit by bit. So bit by bit. So these instructions perform bit logical operation. For example, the end operation. So RISC-V also has the instruction called AND. Okay, if we use an AND instruction, then this instruction performs bit by bit AND operation. So what is the bit by bit AND? Like the 0 is 0, 1 is also 0, 1 0, 0, 1 1 is 1. Okay, so that is the AND operation, AND logical operation. This operation is performed for every bit. Okay, so that is the bit by bit. So RISC-V also supports these instructions. And then we can use these AND instructions for masking bits. What does that mean? So this is the data, the original data, and then we want to use the part of bit data from this original data. Okay, then we can mask with a certain mask, and we can use the AND operation. So in this example, if we AND this data and this data, and then this is the bit by bit AND operation, then we can just get the part of the first data, okay, the result. So we can use the AND operation. And OR. So OR is also simple. So I believe everyone knows about the OR operation. So we can combine some bit data using. So this is also example. So F234 and 0 0 0 and then 0 0 0 1 2 bit C. If we want combine this first 4 digits of a hexadecimal number, and then if we want combine the last 4 digits of this hexadecimal number, then we can use OR operation, right? This is the OR operation and exclusive OR. So exclusive OR means that if the 0 0, this is 0, and the 1 1 is also 0, 0 1 1 0, this is the 1. So this is the logical exclusive OR. So what is the meaning of exclusive OR? The meaning is if 2 bits are the same, then the result is 0, and then 2 bits are different, then the output is 1. That is the meaning of exclusive OR. So using this property of exclusive OR, we can perform NOT operation, so invert operation. Actually, we frequently use this exclusive OR parity data, actually. So we frequently use these parity data for checking errors in our data, okay? So also we can use the exclusive OR for generating parity bits. Okay, so let's see the example of logic. So this is the examples of logical instructions. And as you can see, the format of these logical instructions is similar to the destination and source 0, source 1. Okay, and then actually the form is the same. So this is represent the destination register, and then these 2 operands are source registers, like source 0 and source 1. So what is the meaning of this logical instruction? We can read data from the source registers like S1 and S2, and then based on the instruction, then the RISC-V performs logical bit by bit operation. So for example, this is the AND. So we can just perform AND operation for this bit. Then the result is 0. So this is the example of the logical instructions. So actually the format is the same to the arithmetic instructions, and then you can just identify different logical operations using different instructions. This is the regularity of the RISC-V instructions. Also, we can use immediate instruction. So what is the immediate instruction? We can use one over source operands as immediate numbers, right? So constant. And then the RISC-V instruction, this immediate number is the 12-bit 2's complement, right? That is a 12-bit 2's complement. So you see the format of this immediate type logical instructions is also same to the immediate time arithmetic instructions, right? Like the add I. Okay, add I has so also it has the one source register and then no one destination register and then one source register and immediate number. So this register has 32-bit data. So the 32-bit RISC-V computers. So this source register, like T3 has 32-bit data. But we know the immediate number is the 12-bit 2's complement number, 2's complement data. Then what can you do? Repeat logical operation. So this is 12-bit immediate field, and then this is the 2's complement. So when this immediate number is applied for operation, then extends this immediate number using sign extension. MSB, the most significant bit is extended. So it fills the remaining part of this number. So in this case, the MSB of this number is 1 because this is negative number, right? It's a negative number, then the sign bit is 1, so which means then the MSB of this immediate number is 1. So we need to fill 1. We need to fill these bits using 1. Okay. Logical operations. So if the immediate logical instruction, then we need to know that this immediate number is the 12-bit 2's complement number, and this 12-bit 2's complement number is used for the arithmetic or logical operation. Then we need to apply sign. You need to remember. And shift instruction. Shift instruction means that the bit positions, like the 1 1 1 0 0 0 0 0. The bit position can be shifted into left side or right side. That is the definition of shift instructions. We can change the bit position using these shift instructions. But we already know that the RISC-V, the 32-bit RISC-V computers has, of course, the 32-bit data in a register, right? So actually, which means that the maximum amount of shift is what we just apply the 31. Okay. So for the shift instruction, then shift instruction also use the shift amount stored in this file or immediate number. For shift instruction just use the lower 5 bit stored in the register. So which means we can just store very large number, such as the 128 in the another source register as one. But this is invalid because what is the 128? 10000, something like this. And then actually the lower 5 bit is just 0. If we just shift some source register using this number 128, but the result is shift by 0 because the lower 5 bit is just 0, right? So actually the shift operation is not performed. So you need to remember that when you apply the shift operation, then the shift instructions just be 5 bit of 5-bit data stored in register. So the shift instructions can also use immediate number. It's also the same. And the shift instruction is applied only lower 5-bit of immediate data is used. Okay. So let's see the operations of shift instructions. So first instruction is SLL. So it means shift left logical. Okay. So it means that it's the bit position is moved to the left side. Okay. So this is the example, and then we for the some remaining part using zeros. So for example, this is the example. So 1110, and then if we just apply shift left by 2, then what will happen? So if this is 4-bit data, then 10 because it goes to 2-bit. It goes this bit is shifted left by 2, and then this bit is also shifted left by 2. Then we have 2 empty bits, right? It's shifted. So for the empty bits, we can just zeros. Okay, this is the shift left logical. For the shift right, we can just RISC-V has 2 different instructions: the shift right logical and shift right arithmetic. Why? So it is because what is different? If we use SRL, so SRL represents shift right logical, then this is the shift right, and then so it's a shift right, so it's a 1110, and then we just perform shift right by 2. Then what will happen? These bits are shifted by 2 bits, so 1 1. Then we have 2 empty bits. So if we just shift right logical, then RISC-V insert zeros for the empty slot. Okay, the shift right logical. But if we just use the arithmetic, then these empty bits are filled with the MSB, just sign bit. So in this case, the MSB is 1, right? So it is filled with the 1, right? Arithmetic. So the difference is that the empty bit can be filled with the zeros, right? It can be filled with the MSB, so bit. Okay. And then, as I mentioned, the shift instruction has also like the SLLI and the SRLI. Okay, so then we can use the immediate number. But as I mentioned, we need to use the immediate number between 0 to 31. Okay, the number is shift instruction, right? Okay, this is the shift instruction. So we can manipulate. So we can make something by bit operations using logical instructions and shift instructions. And especially, so we frequently use the instructions for performing multiplication and division. Why? Because this is the computers binary number, and then if we just perform multiplied by 2, so 2 is the power of 2, or multiplied by 4, or multiplied by 8. So these are the powers of 2. 4 by power of 2, then we can replace this multiplication using shift operation, right? So for example, multiply by 2, this is the shift left by 1, right? So, and then our benefit is that the multiplication is actually heavy job. It requires very large hardware components, but with using the shift operation, we can just use the very simple hardware shifter. Okay? This is very simple. Okay? So division is also same. So if we just perform the divided by 2 or divided by 4 or divided by 8, then it can be replaced with the shift right. Okay, so shift right 1, the shift right 2, and shift right 3. Okay, this is because the computers handle binary number, then it means that the multiplication or by the power of 2, and we can replace these multiplications or divisions into shift operations. Okay. So this is the shift instruction. Okay, it's very simple. I believe. Okay, just the behavior of shift instructions or logical instructions. So now let's learn about branch. Okay. So if you hear these terminologies like the branches or jobs, what can you think about? So what think about these branches or jumps? So what are branches? The branches it's a tree, and then tree has the many branches, right? So the branch means that actually a certain branch can be divided into the multiple branches, right? So it's called the branch. Okay. Then what are branches in a program? Branches in computer instructions. The typical example of branches in our if else, right? So if a certain condition and A is executed, and then else, then B is executed. So why is this a branch? It is because until here we learned the programs are executed from to bottom, right? So actually, if you think about the RISC-V software, the RISC-V instruction, then you can observe that the instructions are executed from top to bottom sequentially, right? But how about if else? Based on the condition, so this condition, then when the computer, based on this condition, computer needs to execute A or B. So which means the instructions are executed like this from top to bottom, but at this point, the if point, then it can execute the different instruction like A or B. That's why this behavior is called a branch. Okay, like the branch of a tree, the execution path is divided into the two different paths. Okay, that's why it's called branch. Then what is jump? So jump is just jump. So from this point, we can jump to the another point. Then we can skip this point, right? This is also same to the RISC-V instructions. So instructions are executed from top to bottom. Then jump means that, oh, we can jump to the another point. Okay, this is the meaning of jump. So firstly, understand the meaning of a branch and meaning of jump in a software, right? So let's start. So branch instruction. So as I mentioned, branch instructions change the execution path or sequence. Okay, so like this. So if instructions are executed from top to bottom, then at this branch point, then instruction. So this software can execute different instructions, A or B. Okay, that is the branch instruction. Then how can we implement a branch? Think about the stored program. So what is a stored program? Stored program means that instructions are stored in a main memory, right? So these are instructions. Okay, and then the address of a certain instruction is program counter. Okay, and then when an instruction is executed by a processor, then program counter is just changed from this point to this point, this point, and this point sequentially, right? And then let us assume that this is the instruction A, and then this is the instruction B. And then I already explained that the branch, then so A and B. So based on the condition, then this program can execute the instruction A or B. But we already know that instructions are stored in the memory like this. Okay, then how can we perform this branch instruction? So let us assume that this is the branch point. Okay, it's a branch instruction. And then based on a certain condition, then the next piece. So next instruction can be A, or the next instruction can be B, right? So it means based on the condition of this branch instruction, the next program counter can be here or here. Do you understand? So in a stored program, instructions are stored in a memory, and then the execution of instruction is pointed by program counter. So the branch instruction just change the next program, next PC. So which means the value of program counter for the next instruction. You understand? So by changing the PC, okay, so it's the PC program counter of the next instruction, we can implement a branch behavior. Okay, so you need to understand this. So until now, we learned about many instructions, like the arithmetic instruction and memory instructions and then logical instruction. Then what is the target of these instructions? The destination is the register file for the most instruction, and the destination of store instruction is the main memory, right? For the branch instruction, target, that means the destination. Destination of branch instruction is the PC, okay? Because we need to understand this. The branch from other normal instructions. So as I mentioned, instructions change the file or memory. The store instruction only changes the memory, but branch instruction changes program counter. Okay. So there are different kinds of branch instructions, like conditional branch or unconditional branch. Unconditional branch instructions are just called the jump instructions. Okay, so typically these are called the branch instruction. Okay, but we can also call this is branch. This is the branch, conditional branch, and then this jump instruction is the unconditional branch. So unconditional branch is just simple. So branch instruction means that, based on the condition of the branch, then PC can be changed to the A or B. Okay, there are two different program counters. There are two different target program counter values for this branch instruction. But jump, that is the on. So which means that a processor does not put down condition. There is no condition, right? Just jump to the different PC. Okay, that is the unconditional. So RISC-V supports the four conditional branch EQ. So it starts from B, and then on these two represent the condition. Okay, so B represents the branch. Two letters condition. Okay. So BQ, that is the branch if equal. Okay. So we can understand as the representation of the name of a branch instruction. So branch if equal. So which means that if equal, PC is changed to the target of the branch. Okay. Then you may think that, it is, so this is the branch, and then the next target can be A or B. Then what is the target of a branch? So branch instruction looks like this. So branch and condition, and then the target. And this is the condition. If the condition is true, it jumps to the target. All right. So it's a can jump to the B. Okay, if the condition is false, then what is the target? The target is just the next instruction. So which means that if the condition is true, then it jumps to the target. Else, next instruction is executed as normal. Okay, that is the meaning of a branch instruction. Then if we understand that this meaning, then you can understand the behavior of branch. PQ equal branch, and then PME, it's not equal BLT, branch if less than BG, branch if greater than or equal. Okay. So based on the this is the definition, and then based on the definition, then we can just understand the branch instruction. Okay, and then jump. So there are also different kinds of jump instructions. We learn about these conditional jump instructions later. But to understand that there are also different kinds of jump instructions like jump register, and jump and beat. So this is for the unconditional jump instructions, we will learn the next class. Okay, so let's see the example of conditional. So where is the conditional branch instruction? Here, the BQ. Okay. So and then as I mentioned, a RISC-V processor execute instructions from top to bottom. Then these are very simple instructions. Like so, S0 has the 0 plus 4, so because it add I, and then 0 plus 1, and S1. So we use the SLLI. So this is the shift left logical immediate. So it's SL shift left by 2, it becomes 4. Then this is the branch instruction, BEQ. So what is BQ? This is the branch if equal, right? So what are compared then? So if you see the conditions of a branch instruction, then you can find equal, not equal, then less than, and then greater than or equal. So it means actually branch instructions need to compare two data or two operands, right? So as you can see, BQ has the two source registers. So BQ, other branch conditional branch instructions use two source registers as operands. Okay, so we can just compare the data in this, right? So, and then the S1 has S0 has 4, S1 has 4, so which means this is equal. Okay, so and then you can find the target. So that is the target of branch instructions. Then where is target? You can find the target here. So this is called the label. Okay, it's a label. RISC-V assembly code, and you can find the labels like this. So you can find the labels like the main has function names like this. So actually label represents the target of branch instruction. Okay. If you can see this branch instruction, the target is this here. The target of this branch is target. So it means the label is here. The label target is here. So which means if the branch condition is true, okay, so it's called the taken. Okay, if the branch condition is true, it's called or taken. So or taken branch. Okay, so we can say that our branch is taken because the condition is true. Okay, it jumps to the target. So this instruction is executed. So, and I mentioned that actually this target is to be PC of this instruction. Okay. So actually you can find the label name here, but actually in a real RISC file, this target is calculated using the program counter of the instruction. Okay. You can just understand that this is target, and if the branch condition is true, then you can jump to the target of this instruction. So, so you can program or not. So branch is here. Actually, it's the same here. Okay. So and then you can find that this is the B and E. So actually, this is the example of a taken branch. So taken. Then this is the example of not taken. Okay. Why? We use the B and E branch if not equal. Okay. And then we already know that S0 is equal to S1, but this B and E, so inequality of 0 and S1. Then if the S0 is not equal to S1, then this program jumps to the target. But we can find that this is not taken. So if the condition is false, then this is called not taken. Okay, so you need to remember this. Okay, because I will frequently use the taken branch or not taken branch later. Then what will happen? So as I mentioned, if the branch is not taken, then this branch does not jump to the target, does not jump. So which means next instruction will be executed because the branch does not jump to the target. Okay. So this is the example of not taken branch. The condition is false. Branch after the branch instruction, the RISC-V just execute the next instruction, very next instructions, right? So based on the branch instruction, the behavior of branch instruction is important result. If the condition is true, then jump to the target. And then condition is false, then execute the next instruction. So this is the behavior of computational branch. And typically, this is also called a branch. Okay, simply called a branch. Also, let's see the unconditional branch. Conditional branch is actually very simple, right? You need to consider about the condition of the branch. So, for example, this is a jump instruction, and then jump instruction has only one target. Okay, target. Where is the target? Target is here. So regardless of the condition or execution path of this instruction, then it jumps to the target. The example of unconditional branch. Okay. And then let's the example of branch instructions using the C statement. C syntax statement. Okay. So high-level language code we frequently use if statement or if else statement. So that is the conditional statement, right? And then we frequently use the while loops or for loops for iterative instructions, right? And then let's see the example of RISC-V code of these statements. Okay, if statement. This is the C code. So which means if the I is equal to J, then this is executed. Okay. Then then this is executed. So what is this code? So based on the condition, then this can be executed or not. That's it. So this instruction is commonly called code into the RISC-V assembly. So we can use the branch instruction, okay? But as you can see, if equal, then this is executed, okay? But then we can find some f equal g plus h after the branch instruction, okay? So these are also can be translated into the another instruction here, and so we can find the f equal f minus I in the next instruction. So what this behavior, if I equals a, then this will be executed. So in this case, we need to check the I is not equal to j. If the I is not equal to j, then we just skip this instruction, right? You understand? Then we just execute the jump to the f equal f minus I. So if I equals j, so this if statement check the equality between I equals j. But then I also explained, this is the branch. So it can be translated into branch instruction. And then f equal g plus h, we can use the add. And then f equal f minus I. So we can use the sum. So based on this condition, if it's true, then this instruction is executed and this instruction is executed. So which means, this branch is not taken. If a branch is not taken, then f equal g plus h is executed. F equal f I is executed. If the branch is taken, then it jumps to the f equal f minus I. So only this instruction is executed. So it says if the C code is translated, then we need to check the I is not equal to J. Okay, so this is the example. The BNE, we use the BNE code. We need to check the I is not J. So if the S3 is not equal to S4, okay, it compares the in S3 and S4, then jump and 1. Okay. Then if it's equal, then two statements, this statement and this statement are the if statement. And then we frequently use the if else statement right here. If I equal j, g plus h, f equal f minus I. So like the same way, so it's a little bit different, but we can use the same branch instructions, right? We can just check the I equal j. So which means we can use the B and E, and then we just compare the S3. And then if these are not equal, okay, these are not equal, then we are if okay. If I equal z, okay, I equal z, then we just g plus h. Then this code is here. Okay, so which means we check the I is not j, I is not equal to j, and then if it's not true, so which means that I is equal to j, then this is executed, right? And then we can find the unconditional branch. Why? So here, the target of this jump is here. So after executing this add I, if there is no unconditional jump, so what will happen? If this line is removed, then what will happen? This instruction is executed, and after that, this instruction is executed. So it's different. The behavior is different. So we want to execute this line only if the I is equal to 0. So actually, after this instruction, then we need to skip this line. Okay, so it's done. Okay, so it looks like this. So the Bn is here. Okay, Bn is true, A is here, and then A is here, and then jump is here, then B is here. So after A is executed, then it's jump to this done, label is done. And then if this condition is true, then it goes to B, and then it goes to the done. It looks like the branch is here, A is here, and then it is converged at done. Okay. Actually, it's I think very simple, and we frequently use this in our code, right? But actually, in order to execute this if else statement, we require conditional branch and jump. Unconditional branch. Okay. Then also we actually we use the branch instruction, the if and jump, to implement the if else statement. Okay, then let's see the while loop. So this is the example, and then if this is the condition of the while loop. So if the condition is true, then it's repeated again and again, jump to this point, and then the condition is false, then it executes the next statement. So out of the while loop. Take statement out of the while loop. Okay. So if you see that this while statement, then condition is true. Okay. So this is the condition. And then if the condition is true, then these instructions are executed, right? And then if the condition is false, and then it jumps to this point, it's done. So if we see the while loop, it's similar to the branch instruction, right? So, but only difference is at this point, then it surely returns this instructions are executed, and then it jumps to the while loop of the while. How can we implement this while statement RISC-V assembly? So we can find the while loop here, okay? And then also, as I mentioned, the condition is true, then jump, then skip this instruction. And then if the condition is false, then these instructions are executed. So as we learned about the if, the condition should be inverted. That's why we use the BQ here. So you can find the not equal. In the RISC-V assembly code, we can find the BQ. So So if the S0 is equal to T0, what will happen? The target of Y is done. Then, oh, it's done. Okay. And then this inside of the while loop is skipped. If this is false, then this is executed, and then you can find the jump instruction here. You can find the unconditional jump. This is how the while statement is implemented. For it's the same. Okay. So we also frequently use for statement. So you can find the B to here, and then B to the true, then it's done. And then these the inside of the for loop is here. So these are instruction, and then you jump to the for condition. Okay, so it's very similar to the while loop. So this is the another example. Okay, so you can find the PC here, and then J group here. So these C statement, so but the if statement and Y statement and then for statement, and then we can easily understand that these instructions are just translated into the RISC-V assembly instructions. So we need to know that when this is the condition of the for loop, also while loop has the condition. So if statement has a condition, when the condition is checked, then we need to use some opposite condition RISC-V, because RISC-V, right? If the condition is true, then it jumps to the different location of the program. So which means that these instructions are skipped. Okay, do you understand? So actually, but when this iterative loop is implemented, then if the condition is true, then the instruction inside of this loop is executed. Which means that this is the instructions inside of a loop. So if the condition, so in order to make these instructions executed, this condition needs to be false, and these are executed. Okay, so when we write the RISC-V assembly code from, we need to consider the property. Okay, understand? So this is another version of the for loop. So you can check this one. So actually this code used some different instruction in the SLT. So SLT means the set if less. Okay. So which means that if the condition is true, then this is the target register, and target is set. Okay, target is set. Then what is the set or reset? What does that mean? So set means that actually, so it means that we store 1 or non-zero value is the set. Reset is store 0. Okay. So which means set if less than. So which means if the condition is less, the condition is true, then it's set. The register, the target register is set. Which means we just store 1 to the register. Okay, we can use this SLT instruction, and then also you can find that BQ is here. Then the BQ is just to compare the target of SLT with 0. Okay, so then I mentioned that the branch instruction, and we need to compare two different data in register file, right? The equal is actually simple, right? If the A is equal to B, so which means actually, so these are two binary numbers, right? Binary numbers in, so equal actually, equal means all bits, all bits of this, this number. But in order to check the equality between two binary numbers, then we can check the equality of each bit, the bit by bit equality. Then if all bits are the same equal, then we can know that oh, these two values are equal. Right? So this is same. So 1, 1, 1, 1, 1, 1, 1, 0, 1, 1, 1, 0. We can just compare the bits. Which one is actually the same? And then n is also simple because it means the not equal. So it's the inverse of the equality. But we can also find the BLT and BGE. So which means that actually these two instructions need to compare magnitude of two different numbers, right? BLT means that A is less than B, and then BGE means that A is greater than B or equal. So which means the data stored in A or B can be signed data or unsigned data, right? So which means if we use the BLT or BGE, then we need the stored data. Which means that no, the stored data is unsigned data or signed data. Right, obvious, right? So if we perform, can use the BLT and BGE. So which means that we just compare the data. But we assume that these data store signed numbers. And then if we just compare the unsigned data, then we need to use the BLTU or BGEU. So default is the signed data, but if we just perform unsigned comparison, GU and then BGEU. So this is the example. So X22 has the 1, 1, 1, 1, 1. X23, 0, 1. Then if we compare the X22 and X23 using the, and then if we assume these two numbers are signed numbers, then X22 is less than X23 because this is negative number, right? This is less than 0. And this is positive number. And then obviously negative number is less than positive number. So it's the result, the condition of this comparison is X22 is less than X23. If we just perform sign comparison, actually this is very large number, right? All ones, okay? It's a very large number. And then this is just 1. So it means that X22 is X23. Okay. So this is we need to distinguish a comparison is signed comparison or unsigned comparison. Okay. Okay. Then actually this is a very important concept. So let's learn about the basic blocks. In this, we learned about branch instructions and jump instruction. And then I explained that branch instruction or jump instruction change program counter. It means that the program counter is changing. So it means instead of PC becomes the next PC of the next instruction, then PC value is changed to the some different values. Okay? It jumps to the different values. Okay? Then we can define each flag means if a certain instruction is executed and then within a basic block, so inside of the basic block, the instructions are executed from top to bottom sequentially. Okay, that is the meaning of a basic block. So why? Why do we need to learn about the basic block? Because it's very critical for the performance of computer processor. Right? Then actually in chapter 4, we will know processor. Then actually the pipeline, the performance of pipeline processor is degraded because of branch instructions. Okay? So we'll learn later, but it means that the branch instructions are found in our program code, then our program code will be executed from top to bottom sequentially without any branch. In this case, then performance can be high because the cycle is not wasted. But if there are many branches, then the program can be executed like this, or jump and jump, jump, and then jump to the another point, something like this. In that case, the cycles are wasted, performance is increased. So that's why the basic block is very critical for the performance. So we want make basic block size large. And so this is the definition of the basic block. The definition of a basic block is the sequence of instructions and then no embedded branches. So which means that basic block just include branch instructions at the end of basic block. This only, okay? And then there is no branch target inside of the basic block except at beginning. So the target is only found the first line of basic block. So you remember this. So target of the branch is located at the top line of the basic block. And then branch instruction, including jump, is found only at the last line of basic. Then this becomes a basic block. So which means if this instruction is executed, then following instructions are executed serially until the last line of. Okay. So that is the basic. Then, as I mentioned, basic block is very critical. So if the basic block size is large, then the performance is better. Unfortunately, a typical basic block size in our program code is around 4 to 5, which means that we can find branch instruction every 4 or 5 instructions. The size is very small. It's also very critical for the performance of compiler optimization. A compiler actually can apply optimization technique inside of the basic. Okay, so I will stop here, and then I hope you can easily understand the concept of branch instruction. The next class we will learn about the function calls. Okay, sir? Okay, thank you for your listening, and then see you in the next class.